Hello everyone, my name is Mihir Thakkar and I welcome you all to our Introduction to Computer Programming course at Code Heroku. We at Code Heroku are trying to make world-class computer science and engineering education accessible to millions of students out there, and especially in developing countries like India. In our previous class, we have seen how you could use transistors to build digital logic. We can store either a 0 or a 1. But wait, can't we represent bigger numbers using transistors? We definitely can, but the question is how. In our today's class, we'll try to answer this question. We'll go over the concept of bits and bytes and also study some number systems. And then we'll zoom out a little and study what makes up a computer. And finally, in the hands-on section for the day, we'll write our first C program. We'll take the input from the user and print it on our screens. For most physical quantities, it is much more convenient for us to group the smaller units to form a bigger unit. For example, when someone is asking you your weight, you won't tell them my weight is 50,000 grams. You're much likely to answer about your weight in pounds or kilograms. Similarly, in computing, it's much more convenient for us when we group the smaller units bits to form bigger units such as bytes and kilobytes. For example, we take 8 bits together and form a bigger unit which is called as bytes. You could combine thousands of bytes together to form a kilobyte and so on. So my question to you is, how many bits make up a 1 megabyte? Remember, the purpose of this course is not to teach you a lot of facts and information. So I'm not going to tell you the answer to this. You will have to look it up on Google. In today's world, information is so much accessible that no one actually cares about how much facts do you know. But what people do care about is how can you apply that information and solve their problems. As we saw in our previous class, by using transistors as electronic switches, we could implement logic and also store bits of information. But is that it? Can't we store bigger numbers on a computer? You definitely know that it is possible, but my question to you is how? As a hint, try to correlate this with numbers that we use daily, wherein we have digits only from 0 to 9. So here's what we do in our daily life. We club digits together to form bigger numbers. Simple, right? For example, let's say we want to say 129. So we would write it as 1, 2, 9. One thing to notice over here is, at every position in this number, we assign weights. That is, we multiply this number by 1, this by 10, this by 100, and so on. That is, you could write 129 as 1 into 100 plus 2 times 10 plus 9 times 1. That is 1 times 10 raised to 2 plus 2 times 10 raised to 1 plus 9 times 10 raised to 0. This form of representing the numbers, wherein we have weights in the powers of 10, is called the decimal number system, which comes from the Greek word deca, which means 10. So in our daily life, when we use 10 digits from 0 to 9, it becomes convenient for us to use a number system with powers of 10. But in the world of computers, we only have either a 0 or a 1. So it makes sense to use and represent numbers in the power of 2. So in the world of computers, let's see how will you represent something such as a number 7. We already saw that we'll be using powers of 2 over here. So what should we put in these brackets so that it represents the number 7? So let's try to figure this out. 2 raised to 2 is 4, and to get to this number we need at least 4 plus, I'm looking for another 2 at least. Yes, so I would add a 1 multiplied by 1, and I'm looking for another 1 now, and 2 raised to 0 is 1, so I need that as well. So this will give me number 7. This form of representing the numbers in the powers of 2 is what we call as the binary number system. Therefore, 7 in our decimal number system is equal to 1, 1, another 1 in binary form. So here's your quiz. Convert the number 11 in decimal to its binary equivalent. Here's the solution. For number 11, we want to start with at least 2 to the power 3, which will give us 8, and so on until 2 to the power 0, which will give us 1. So, do we need 8 to get to 11? Yes, we need it. Plus 4, but that will get us to 12. We don't want 4. Do we need 2? Yes, we need another 2 at least. That got us to 10. Do we need another 1? Yes, we do. So, 11 to the base 10 is 1, 0, 1, 1 to the base 2. So here's another way that some people use, and especially this is useful for bigger numbers to convert them to binary form. Let's say if we had to convert the same number 15 in the decimal to its binary representation. The trick over here is to divide the number by 2 and capture its remainder until we get the quotient as 0. For example, 15 divided by 2 gives us 7, remainder as 1. 7 divided by 2 again will give us 3, remainder as 1. 3 divided by 2 will give us 1, remainder as 1 again. So we can't divide 1 by 2 anymore. So we'll say 2 times 0 and we have the remainder as 1. And so the result is 1, 1, 1. That is 15 to the base 10 is 1, 1, 1. Note that we started counting the remainders from bottom to top, not the other way around. So this one is actually this guy. So another important number system that we often use in computing is called the hex number system. Here we represent numbers in the powers of 16. Here not only we can have digits from 0 to 9, but also additional symbols in form of A, B, C, D, E and F. That is, we'll represent the number 10 as A, 11 as B, 12 as C and so on, 15 as F. So let's see how we can represent the number 20 in decimal format in hexadecimal form. So we already said that we are going to use powers of 16. So to represent the number 20, which is greater than 15, we'll definitely need more than one hexadecimal symbol or a digit. So let's do the same thing that we did for representing the binary numbers. Over there we could use only 0 or a 1, but here we could use all the digits from 0 to 9 as well as additional symbols from A, B, C, D, E and F. So let's see. To reach to 20, do we need 16? Yes. So what should I write in this bracket such that we get at least 16? We can't write a 0. We can write a 1. If we write a 2, we'll reach to 32 and that will be too high. So let's go with 1. So we have 16 and we need 4 more. 16 raised to 0 is 1 and 1 multiplied by 4 will give us 20. So 20 in decimal number system is equivalent to 14 in hex. And we could have done the same using the second method that we saw for binary number systems. Instead of dividing the number by 2, this time we'll divide the number by 16. 20 divided by 16 will give us 1 and the remainder will be 4. 1 divided by 16 will give us 0 because we can't divide 1 anymore. and that will give us remainder as 1. And then we write remainders from bottom to top. And as you see, we got the same result. So let's convert a bigger number this time. Let's say if we want to convert the decimal number 65535 into its hexadecimal equivalent. So we'll start dividing the number by 16. 65535 divided by 16 will give us 4095 and the remainder will be 15. 4095 divided by 16 will give us 255 and the remainder is 15 again. 255 divided by 16 will give us 15 and the remainder will be 15 as well. And 15 divided by 16 will be 0. The remainder will be 15 as well. And when we have two digits as remainder, we convert them to its equivalent hexadecimal notation. Remember we said that 15 in decimal is F in hexadecimal number system. So we will convert all these 15s to Fs and thus the result will be FFFF hex. So here's the quiz for you. Convert the decimal number 4335 into its equivalent hexadecimal notation. So just like we did last time, we'll start dividing the number by 16 again. 4335 divided by 16 will give us 270 and the remainder will be 15. 270 divided by 16 will give us 16 and the remainder is 14. 16 divided by 16 will give us 1, the remainder is 0. 1 divided by 16 will be 0 and the remainder is 1. And as we did last time, we'll convert anything with two digits to its equivalent hex number. So 14 will become E, 15 will become F, and so the answer is 4335 in decimal number system is 10EF in hex. So now you have some idea on how things work at the lowest level of a computer. We have studied a thing or two about transistors, gates, number systems, etc. But now let us zoom out a little and see how computers work at the highest level. And remember, throughout the course we are going to do this several times. We will zoom in and zoom out to understand the complete picture. And this also happens to be an important concept in computer science, which we call abstraction. We look at a problem at different levels until it all makes sense together. At the highest level, we can imagine that every computer has at least one central processing unit, or the CPU. This is the brain of the computer. It does all the calculations and the actual work that it needs to perform. Each computer will also need some memory. And there are two types of memories that computers usually have. The first one is called the RAM, or the random access memory. The second one is ROM, which is the read-only memory. Property of RAM is that it is volatile. That is, it can't keep an information once you turn the computer off. Whereas on ROM, you can store the data permanently. Next, most computers also have some form of an input and output interface. So these allow the computers to communicate with the outside world. So you could interface things like your computer screens or your keyboards or your USB devices. And you also need some form of communication between all of these, right? So this is achieved through what we call the system bus. So think of them as a group of wires which are connecting each of these blocks. And by wires, I don't necessarily mean those strands of wire that we usually talk about, but these are generally a group of tracks on your PCBs which connect each of these blocks together. And in the end, we also need some form of synchronization between all of these units, right? They have to work with each other. This timing unit generates this signal which we call as a clock. Clock is nothing but ticks that all of these listen to. And as I told you, CPU is the brain of the computer. So let us see what all it consists of. A CPU is made up of two components, an ALU, or the arithmetic and logical unit, and the control unit, that is the CU. The ALU performs the actual operation that the computer needs. That is, it could be addition, subtraction, multiplication, or whatever it is. And the control unit actually tells the ALU what operation to perform. So here's your quiz. So in the high level block diagram of a computer we just saw, where do you think will a speaker connect to? Will it connect to the I/O interface? Will it connect to the memory unit? Or will it connect directly to a CPU? And the correct answer is it will connect to the I/O interface. Remember, all input and output units connect to the CPU through the I/O interface. So now let's get into the hands-on part of today's session. If you haven't already installed the C compiler on your machine, I recommend that you do that now. Please read the description below for details. So let's start writing our first C program. I'm gonna say this is my first C program. So in C, when you start a line with 2 slashes, the compiler will ignore anything after that. And these are called comments. And especially when there is more than one person working on it. So it is always good to add some comments to your code so that when you look at the same code after 1 year, or let's say if someone else is looking at your code, they can understand it as well. So now we are going to say hash include stdio.h. In C, the lines which starts with the hash or the pound sign are special. So these are not the instructions for your machine, but these are the instructions for your compiler. And what we are telling the compiler over here is take this file stdio.h and paste it over here. stdio is the standard IO. IO is input and output. And it has the functions like the printf and the scanf that we are going to see further. So the next thing that we want to do is write our actual program, and that we do inside the main function. So we are going to say int main and then brackets, and then we are going to have a pair of curly brackets. So C is one of those languages which uses curly brackets to group things together. So essentially what we are saying to compiler is everything that is within these curly brackets is part of the main function. Makes sense, right? So just like we saw before, let's print something out to the screen. And if you remember, the name of the function was something called as printf. So let's say something like I have %d number of apples, and then we're gonna say 8. So what we are telling the compiler to do is take whatever number is over here and put it inside this sentence, the place where we have this %d, which means an integer. And because we said that this is an int main, which means we are gonna return an integer, and as we promised, let's return an integer to the operating system. So you could return any number from here, and it's up to the operating system to decide what to do with it. But the normal convention is to return a 0 for a successful execution, or 1 or even higher numbers to indicate some failure. So now let's run this and see if it works. So over here, I'm compiling these programs on my Mac, but it shouldn't be any different than compiling it on a Windows PC. So if you are using a Windows PC, you can check the description of this video where we show you the steps of how you will compile a C program on a Windows machine. So let's try to compile this, and to do that we'll say gcc, which is the name of our compiler. We'll say -wall. Now I'm not gonna tell you what that means. I want you to look that up on internet and find out for yourself. Remember, one of the goals of this course is to make you a good problem solver, and to do that you need to have some research skills as well. So I want you to think like a scientist and not just take whatever I say. So go to the internet and find out why am I using -wall, and maybe you can share that with your other friends in the comments below. And then we'll have the name of the file, which is hello.c, and then we'll say the name of the output by using -o. The name of the output file we want is hello. So that compiles without any error. Let's try to run this, and you can run it by using /hello. There it is. It says I have 8 number of apples. But this is a boring program, right? I mean, there isn't much useful that we can do with it. What if the number of apples that I have change every day? What if someone gives me new apples? So instead of directly printing it out over here, let's create an integer which will store the number of apples that we have, and then we'll print that out. So what should we call it? Let's call it num apples. Int num apples is 8. Now instead of writing 8 over here directly, I could say
num apples. So this is similar to what we did in the machine code, right? When we had to put a number inside a memory, and this is what we are doing over here as well. So let's see if this works. So we are gonna compile it again, and then we are gonna run it. So as you see, we got the same result, but this time instead we are storing this number in a memory somewhere. So let's do more interesting stuff with our program. So let's say if someone took one of the apples that I had. So let's see how we can say that to our program. So should we say something like int num apples equals to int num apples minus 1. So let's see if that works, right? So we'll compile the program once again. Oops, what does it say? It says redefinition of num apples. So it is telling us that you have already told me what num apples is. It's an integer. So now every time you want to use num apples, don't give me the int once again, right? So what we should have done instead is just say num apples equals to num apples minus 1. Now let's see if that works. We'll save it and then let's see if that works. We didn't get any red flags, so that's a good sign. Let's see if that works correctly. And there it is. It says I have 7 number of apples, which is what you would expect if I had 8 and someone took 1 away from me. So this is good, but still not that interesting, right? What if we want the users to tell us how many apples they have and then print it out on screen? So let's try doing that. So we'll first get rid of this line which we had over here. So instead of saying int num apples equals to 8, we'll just say int num apples because we don't know how many apples the user has. So let's first ask the user to tell us how many apples do you have, and then we are gonna say scanf. So printf is used to print to the screen, but a scanf can take the user input and store it in our program. So we are gonna say scan an integer for us, right, and store it in num apples. So now let's see if this works. We're just gonna clear our screen. Then we're gonna say compile it once again. So we did get a few warnings, but let's leave that for now as it is. So there were no errors. So it's asking us how many apples do you have. So let's say I say 10, and gives us something called a segmentation fault. So whenever you get a segmentation fault, remember that your computer is trying to tell you that you are either reading or writing from a memory location which you are not allowed to. And it makes sense for the operating system to do that, right? What if your program was modifying something in someone else's program's memory? I mean, it would be a chaos, and that's why it can't allow you to do that. So what went wrong? So let's see if our warnings can give us some hint. So in the first warning over here, it is telling us that something is wrong with num apples in the scanf line, right? So what we want this line to do is to take the user input and put it at a location which we are calling num apples. But do we actually know what num apples is equal to right now? We don't know, right? It could be any garbage value that the compiler chooses to come up with. So let's say if num apples had the value xyz in it, what's happening right now is the computer is trying to write to the location xyz instead of the num apples, which is actually the value of num apples right now. And this might be a little bit confusing to you right now, but you will get a knack of it once we go ahead. So instead of saying num apples over here, what we want the compiler to do is actually store at the address of num apples. And the way you call address in C program is to write an ampersand. So we say scanf, take the user input and put it at the address which we are calling it as num apples. So let's see if that works. So we compile it once again and let's run it. How many apples do you have? Let's say 20. And there it is. It says I have 20 apples.